inverse of the many to one quadratic function, but we didn't quite finish. We didn't get an opportunity to actually do any work. So I just wanted to quickly recap. I don't want to spend too long on this, but I just wanted to quickly recap and then jump straight into a question that I wanted to do, and then a sort of slightly more difficult question which combines two different graphs together. All right, so if you can recall from last time, the problem with the quadratic function is that when we invert it, or we do the inverse, it's no longer a function because it doesn't pass our vertical line test anymore. And we've got around this problem by restricting the domain of the original function. All right, so if we restrict the domain of the original function, we can either restrict it where we look at where x is positive, or we can look at it where x is negative. So either, I'm just going to highlight this again for you guys. I think you remember this from last time. Either we're going to restrict the domain to those values of x where x is positive, or we're going to restrict the domain to those values of x where x is negative. So what that means is that when we do reflect our function over the line y equals x, the inverse is also going to be a function. All right, so over here, our original arm of our parabola would be this one that I'm drawing in green, okay, even though it doesn't look exactly the same. And now the inverse is once I have reflected it over the line y equals x. Okay, so I would end up with that sort of shape. All right, so what's important to note here is that this particular function is going to be described as y equals root x, and that is for where x is positive and where y is positive as well. Okay, then if we do the same thing with the other one, our original arm is going to end up being over here. There's the original arm. Oopsie, sorry, it was a bit skew. That's the one that's in yellow. And of course, when we reflect that over the line y equals x, we end up with that arm over there. Okay, so after interchanging x and y, we would now end up with y equals negative root x. And again, we're considering that part of the Cartesian plane where x is going to be positive and y is going to be negative. Okay, because it's below the x-axis. Did you want me to recap a little bit further about switching x and y around and making y the subject of the formula, or are we all good to go?
Ma'am, I think we're good to go.
You think, okay, all right, that's fine. I just didn't want you to think that I was just whipping through it, but all right, not a problem. Okay, so cool beans. All right, thank you, Johannes. Okay, so the first thing that I wanted to do with you was one question from here. I mean, if we were in class, then ordinarily I'd like to do two, but I think we should just do one, and it'll also give us an opportunity to be able to talk about domain and range for each graph drawn. If you want to, we could do two of them, but I wanted to sort of give you the option. Do you want to do one that's positive, or do you want to sort of focus on the one that's negative? Do you think that that would be, I don't want to waste time doing stuff that you guys feel you already know how to do. Are we happy to do the more difficult question, or you want to do both? Okay, all right, so it seems as though most people are going with both. If you are feeling super confident and you feel that you know how to do the positive one, you are welcome to do the negative one in the meantime. You don't actually have to listen to what I'm saying. All right, so let's get started on that. So the one that I'm going to do with you is this one. Let me just highlight it in turquoise. We're going to have a look at A, so the graph f of x equals 2x squared. All right, so the first thing that they've asked us to do here, let's just change our pen, is they want us to sketch the graph of each function and its inverse relations. You see how they use the word relation and not function on the same set of axes. So when they want us to sketch something on the same set of axes, this really doesn't need to be a work of art. All right, so there's our, actually, you know what, I can use my axes, but I'll just stick with this for now, it doesn't matter. Okay, so now when it comes to us drawing the graph of f of x, oh, that's a terrible parabola, but anyway, there we go. So that would be f like that. And now its inverse relation is going to end up looking like that. Okay, that's what they want from us. Now they've said to us that we need to restrict the domain of the original function in two different ways so as to form new one-to-one functions. All right, so what that means is that either we can restrict it where x is positive or where x is negative. All right, so in question number 2, let's get our axes. Nice pink axes. What we would end up doing is this. All right, so we've got to look at the situation, for example, where x is greater than or equal to 0. So what we would end up in this case is with a function that looks like that. All right. If we restrict the domain of the other one, okay, so in this case here, if we invert that, we would end up with a line that looks like that. Okay, so here our original function would be f, and here our inverse would be that one. So that's the first situation. Then we've got to consider a separate situation. Okay, so now we're going to draw again, let's do a set of axes. I'm just going to make it a little bit bigger. All right, now we have to consider the situation where we are going to make x smaller than or equal to 0. Right, so that means in this case over here, we will end up with the arm that does that. That would be f. And then our other arm, once it's reflected over the line y equals x, is going to look like that. Okay, so we've done part 1, we've done part 2. Sketch the graphs of the new function and its inverse function on the same set of axes. Okay, we've done that as well. Use a separate set of axes for each function and its inverse. All right, so I did that too. We've done that. Hence, rewrite the equation of its inverse in the form f minus 1x. Okay, so as far as this one at the top is concerned, so let's call this 2.1 and we'll call that 2.2. So as far as 2.1 is concerned, that would be the graph of f minus 1x equals. Okay, so now we've got a choice here. We're going to either write positive or negative root x. So this one would be positive root x. Okay, for where x is greater than or equal to 0 and where y is greater than or equal to 0. Everybody happy with that? Okay, for 2.2, we're going to end up with that. All right, for x is smaller than or equal to 0 and in the situation y was greater than or equal to 0 as well, if I'm correct. No, we don't have to worry about that. It's just where x was positive. Okay, all right, that's fine. Okay. There we go. Okay, so that's that one. Right, and then they want us, last of all, to write down the domain and range of each graph that has been drawn. Okay, so in the last bit now, right, so domain and range for f. Okay, so for f, our domain, can you guys tell me what you think that would be? It's actually on the screen already. So we've got x is greater than or equal to 0. Or for those of you that want to write it using interval notation, you could write it like this as well. So it goes from 0 included to positive infinity. That's the other way that you could write it if you wanted. And as far as our range is concerned, okay, y would also be greater than or equal to 0. So you could write that like this. Okay, that's for 2.1. For 2.2, we are going to have, let's change colors here. All right, so for our, sorry, I'm being silly, aren't I? I did. That's the original. Sorry, Matrix, I'm jumping on to the next question already and I'm not even finished this one. Sorry, so for the inverse, all right, it would be exactly the same thing. Okay, y becomes x and x becomes y, so it would be identical. So we would end up with that for our domain and we would end up with that for our range. That is for this one over here, 2.1. Okay, for 2.2, let's put that underneath here. Let's first talk about our original function. Okay, so here we would say that x is smaller than or equal to 0. And as far as our domain is concerned, we would say that y is greater than or equal to 0. Is everybody happy with that? Okay, because the graph starts here at 0 and just continues to get bigger. As far as its inverse is concerned, all right, we would start at 0 and then x would get bigger. So x would be greater than or equal to 0. Can you see how these two have swapped round? Okay, and then we would say the opposite thing for the y. So y is smaller than or equal to 0. Okay, because what was the range is now the domain, and what was the domain is now the range. Okay, does that make sense to everybody? Okay. Cool. Can I move on? Okay. All right, so now let's go back and have a look at the yellow one. Okay, we'll just work through that quickly and then we'll get straight on to that other question. All right, so what I'm going to need to do here, Matrix, is obviously try and rub this stuff off. But obviously, if you wanted to come back and come and watch the video at a later stage, you would be able to do that. Okay. Sorry. I'll just rub all of this off. Okay, and now we can get straight back into this again. Okay, so when it comes to question C, we want to do part 1. All right, so we want to sketch the graph of each function on its axes. So now, Matrix. All right, here we go. We've got a set of axes here, and P of X. Oh, that's not great, but anyway, P of X is going to look like that. Okay, when we now reflect P of X over the line y equals x, what is it going to look like? Okay, hopefully all of you are saying, sorry, I'm going skew here. It's going to look like that. Okay, now I actually cannot write that using functional notation, so I can't label that. That's what it would end up looking like. Okay, because it's not a function. Okay, so what's happened here, all right, is that if we have said that p of x is equal to minus x squared, that means that y equals minus x squared. Thus, if we do the inverse of this, we would have to swap x and y around. So that means we've got x equals negative y squared. Now I need to make y the subject of the formula. I have to divide both sides by -1 first. So I've got negative x like that equals y squared. And now when I want to make y the subject of the formula, I'm going to end up with plus minus root minus x. Now there has to be a restriction on x here. All right, doesn't there? Otherwise we will be talking about something that's non-real. Okay, so this has to be where x is smaller than or equal to 0. Does that make sense to everybody? Because if x was negative, a negative times a negative is a positive. All right, and I need to have a positive inside my square root. Everybody happy with that? All right. Sure, Morongoa, what I was saying is that when we grew the inverse, all right, what we're going to have to do here is we have to restrict this. So this that I'm highlighting in purple now has to be restricted to those values of x that are negative, right? And that is because you've got a negative inside the bracket. Okay, you've got this negative over here. Now remember, you can't take the square root of a negative because the square root of any negative value, whatever it might be, so if it was like -4, we would deem that to be a non-real number. Okay, so that's why when we sub in for x, they have to be negative values because a negative times another negative will give us a positive. So we'll have a positive inside our root. Okay. You happy with that? Okie doke. So now let's draw ourselves some new axes. Okay, and now what we want to do is we want to restrict the domain and draw the graph of the new function and its inverse function on the same set of axes. Okay, so that's going to be our next step. Okay, so if I restrict the domain so that I'm looking at that part of the arm, this is going to be where x is smaller than or equal to 0. Okay, and now what I want to do is reflect that over the line. Let's choose a different color. I want to reflect that over the line y equals x. So now I'm going to end up with, let me just get rid of those guys. I'm now going to end up with that. Okay, so here in pink is P, and here in blue is my inverse. Okay, so this will be or the inverse will be minus x. And then this has to be where x is smaller than or equal to 0. Right, so in other words, once I have subbed in whatever value of x I've now got a positive inside my root, but then I'm going to times it by a negative again because y needs to be negative, okay, because this is sketched below the x-axis. Right, where y is negative. Is everybody happy with that? Okay, and now we can sketch the other one as well. Okay. Let's put that over there. All right, so now remember, we're going to restrict the other arm of the parabola. Okay, so our original function in pink, we're now going to restrict that side over there. So that would be P. And it would be over the line y equals x. So that would end up like that. Oh, sorry, I labeled it incorrectly. Sorry, I beg your pardon. This is P, and that would be P to the -1. Okay, and now here you are restricting this, beg your pardon, to where x was greater than or equal to 0. That's where x was negative, and now we're looking at where x was positive. Right, so as far as our inverse is concerned, this is now going to be positive minus x, and again this has to be where x is smaller than or equal to 0. Everybody happy with that? So I think it's important for you to see what it would look like in its inverse form when the coefficient of x squared is -1 or is negative. Okay, everybody happy with that? So I sort of tried to condense it a little bit and do a bunch of stuff all at the same time. So I've kind of done that, and that all in one go. And now we want to write down the domain and the range. Okay, so in situation number 1, okay, our domain is going to be where x is smaller than or equal to 0. Our range is going to be where y is smaller than or equal to 0. Here for our inverse, it's going to be identical. All right, so here, because it would be the same as that, so x is smaller than or equal to 0, or y is smaller than or equal to 0. Okay, for this one over here, it's going to be different. So let's write down for our range, we have got for our domain, we've got where x, sorry, it's the purple one. Let me just write the correct color here, otherwise I'm going to get myself confused. Okay, purple, we switched over. Okay, so here for this one, this is where x was greater than or equal to 0, and y has to be smaller than or equal to 0. And for our inverse, ach, Yereli, what are you doing? For our original, x is greater than 0, our, yes, smaller than 0, and now for our inverse, we have got where x is smaller than or equal to 0, and where y is greater than or equal to 0. Okay, so again, you've got the situation where your domain becomes your range and your range becomes your domain. Okay, so that's why here my domain says where x is greater than or equal to 0. And that's why here my range says where y is greater than or equal to 0. Okay, and similarly, over here where I said my range was smaller than or equal to 0, that's why for my domain over here, I'm now saying where x is smaller than or equal to 0. Everybody happy with that? Yes, Johannes, they can actually be shifted up and down. That would be like particularly nasty if they did decide to do that to you. But yes, theoretically, they could be translated as well. It's not something that comes up very often, but yes. In fact, I don't think I've got anything here, but I'll try and find something like that with that in it. Okay, but hopefully they don't do that to you. Hopefully. Okay, is everybody happy with that? Can we move on to the other question? Okay. All right, good stuff. Okay, so here was the question that I wanted you guys to try by yourselves. Okay, so we've got the functions f and g that have been sketched, and the two graphs intersect at A. All right, so the first question, so g of x, sorry, is 1 over x, and f of x is root x. Are these two graphs an inverse of one another? Or is f of x the inverse of g of x, should I say?
Ma'am, can you repeat the question?
Sure. So what I was just trying to establish, sorry, Kanyisile, is that g of x and f of x are two different graphs. Even though the line y equals x has been sketched, these two are not a reflection of one another over the line y equals x. They're two different graphs. Is everybody okay with that? Yes, they're not inverses of one another. Okay. All right, 100%. They're not inverses of one another. Okay. So the questions that they want us, and they intersect at A. So the questions that they want us to answer is they first want us to determine the coordinates at A. Then they want us to determine the equation of the inverse of the function f in the form f minus 1x equals. They then want you to redraw the diagram and sketch the graphs. Must be of the inverses, which is a word that got left out. Or sketch the graphs of the following on your diagram. Oh, sorry, beg your pardon. All right, so the reflection of f about the line y equals x, write down the equation of this function. The reflection of g about the y-axis, write down the equation of this function. And then the last thing that they want us to do is write down the reflection of f about the x-axis and write down the equation of this function. Okay, so there's some important bits and pieces going on here. These are the sorts of things that they could ask you in exams. All right, so I'm going to be quiet with Nicole for a few minutes, and I'm going to let you guys work on this, and then we can mark your answers. Okay, if you're stuck or you're not sure what to do, then I'm obviously more than happy to help you. Okay. Yes, Taniko, you're right. Yes, Johannes, you would do that. Okay, so there's a couple of people, that's fine. All right, so let me just give you a helping hand with that because I don't want you to be stuck on this forever. All right, so in A, you're absolutely right. You would have said 1 over x, the hyperbola, is equal to root x. What do you think you'd then need to do to both sides? Or I suppose another way you could look at it, I suppose you could say to yourself, if you consider this, your y coordinate times your x coordinate has to give you 1. So the only way that you can get 1 is by multiplying 1 and 1 together. So I suppose by inspection, really, we could work out that it would have to be 1 and 1. But yeah, if we squared both sides, then we would end up with 1 over x squared equals x. And then you could cross multiply, and then you'd end up with x cubed was equal to 1, and therefore x would be equal to 1. And because it's also on the line y equals x, that means that y would be equal to 1. So there's 2 ways you could look at it. Okay, so the coordinates of A would be 1 and 1. Do you want me to start going through it, or do you want like a couple more minutes to finish the rest of the questions? Okay, Thelma. All right, Botshepo. Okay, perfect. No problem. All right, so the reason why I thought that it is important to have this question in here, this question B, right, is because we are so used to being given the original function and then writing the inverse as the one that is root x when it comes to the inverse of the quadratic function. But in this case over here, the function that they gave us was root x. So that means that the equation of our inverse, okay, we would have to swap these two around. So in other words, if we've got y equals root x, then what that means is that x equals root y. And now I would have to square the left-hand side, and I would have to square the right-hand side, and that means I would end up with y equals x squared. So it's just as, who was it that put it in the chat? Taniko put it in the chat. All right, so in the form f to the minus 1x, it would be equal to x squared. Okay, that's what you should have had for part B. All right, everybody happy with that? Makes sense where it comes from. Okay, then let's look at the next question. So they've asked us to redraw the diagram and then sketch the graphs of the following onto the diagram. So I think probably the best thing for me to do, I'm going to rub this orange off. Hopefully you've all got that down by now, and I'm going to rub that off. And I'm just going to draw on the same graph that's here, but it's just going to make our lives so much easier. Let's just get rid of all of that as well. Okay, so the first thing that they want us to do is they want us to reflect f about the line y equals x. So that means, matrix, that what you should have sketched was this. And again, I'm going to try and get it 100% accurate. Oh, look, it should be a smooth curve. All right, my apologies that it's not. You should have had that. All right, so as far as this one is concerned, that's the reflection of f about the line y equals x. Write down the equation of this function. All right, so the equation of this function, it's going to be what? X squared, or where x is greater than or equal to 0. Okay, everybody happy with that? Okay, the next one, let's do this one in blue. The reflection of G about the y-axis. Okay, so that means that this black line over here, where I've got my arrow right now, is going to be reflected over the y-axis. So it's going to end up looking like that, isn't it? Okay, so if it's been reflected over the y-axis, this is now going to be the well, it'll still be a function, y equals minus 1 over x, because x has changed sign. Okay, and then this is going to be for where x is smaller than 0. Remember, it can't touch the y-axis because that is an asymptote. All right, so that would be the equation of that function. And the last one, let's do it in green. All right, if we now need to reflect f about the x-axis, it's now going to end up looking like that. Okay, and then this would end up being y equals, because we've reflected it over the x-axis, y changes sign, and that's why it becomes negative root x. Okay, and then these are for values of x that are greater than or equal to 0. Is everybody happy with that? Are we all good? So it wasn't supposed to be sort of particularly difficult or anything. All right, lovely. Okay, so what I want us to do now is perfect. Good job. Okay, so what I'm going to do is get started on the inverse of the exponential function, which is called the logarithmic function. Okay, so I want to just talk about that for a little bit, and then we can talk about sketching it. Okay, so when we talk about the inverse of the exponential function, the logarithmic function, what we are doing here is, if we start off with a normal garden variety exponential function like the graph y equals 2 to the x, right? When we now invert x and y, this is what happens. So we've got x equals 2 to the power of y. And because we want to make y the subject of the formula, we have to use logs. Okay, so we would write y equals log, our base is 2, and our number, or whatever it is, would be x. Okay, does that make sense to everybody? So they would expect you to be able to go from just your normal straight exponential function, and if you were asked to write the inverse of that function, they would expect you to be able to do that. So in other words, produce what I've done here in orange. Okay, is everybody happy with that? Okay, so because the graph y equals 2 to the power of x is a one-to-one function, it means that the graph y equals log 2x is also going to be a one-to-one function. So we don't have to restrict the domain in any way, like we had to do with the quadratic function. Right, so the inverse in this case is also going to be a function. All right, so now what does our inverse function actually look like? All right, so if we were to plot that on a graph, we would end up, let's just move these down. Okay, so our graph y equals 2 to the x is this graph over here. Okay, what they've done is that they've just subbed in -1 and worked out the corresponding y, and they've subbed in 1 and they've worked out the corresponding y just to help with shape. The reason that it has the y-intercept that it does is because if we solve for the y-intercept, when we raise something to the power of 0, it's going to be 1. So what's important to note is that when we reflect this function over the line y equals x, what was x becomes y, and what was y becomes x. So please have a look here, Matrix. Can you see this point 1 and 2? It's now the point 2, and 1. What was the y-intercept is now our x-intercept. Can you see how x and y have changed around? And it's the same with this last point over here as well. Okay, what was x has become y. So essentially what we've done is that we've taken a graph that had the x-axis as its asymptote and a y-intercept, and we've reversed that. So now the y-axis is the asymptote for the log function, and it now has an x-intercept. Is everybody happy with that?
Yes, ma'am.
All right. Okay, so it's important to note, all right, good stuff, that if we want to write something in logarithmic form, okay, so I was just putting that there for you as well, we can write number equals base exponent in the logarithmic form as follows. So log base number equals exponent. So that's what I was doing up at the top there, right? Except that I made that the subject of the formula. So if they've given us y equals 2 to the x, that is number equals base exponent. Then when we are inverting that and we've got number equals base exponent, we can now make y the subject of the formula and say log base 2 number. Okay, right, so that's this part over here that I was doing. Sorry, I'm going to highlight that, not scratch it out. Okay, so there's the exponent, there's the log, there's the base, and there's the number. Okay, so yeah, they will expect you to be able to convert between those two in tests and exams. Okay, so I've discussed that with you. So when we invert the exponential function, it's now called the logarithmic function. And where this would be useful to us, I don't know if you remember us talking about this the last time, but this is what they did when they were talking about COVID and about flattening the curve. It was actually a log function that they used. So this was like COVID infections increasing exponentially. And then when all these measures were in place to try and slow down the rate of infections, that's what they meant when they talked about flattening the curve. Okay, so nice to have a real life situation that we can compare that to. All right, now, unfortunately, that is not the only logarithmic function that they would expect you to be able to work with. They want you to be able to work with, sorry, I was playing around with these on the weekend. They would expect you to be able to work with the logarithmic function of this one, so the inverse of this as well. But now the question is, let me just move that down and out the way, is what does g of x equals 1 over 2 to the x look like? If somebody asked you to sketch it quickly, would you know how to do that? What does that particular function look like? Can anyone tell me? Yes, Boichepo?
Ma'am, I want to ask, can you repeat the question again?
Sure, absolutely. So what I'm saying here is, do you know what the graph g of x equals 1 over 2 to the power of x looks like? If somebody asked you to sketch it quickly, how would you sketch it? What would it look like? Does anybody know? All right, so here's another question. If we've got the graph y equals 2 to the x, all right, and I sketched that, it looks like this, okay? If I now want to reflect this graph over the y-axis, right, what would change sign? Well, when we reflect over the y-axis, x changes sign, doesn't it? And that's why, because it has a negative exponent, we would write it as 1 over 2 to the power of x. So it's the same function, it's just been reflected over the y-axis. So it would look like this. Okay, so that would be g. No, it wouldn't cross the x-axis. So your x-axis would still be your asymptote. Okay, so this is an exponential function, but it's a decreasing function. So it's important to note here, all right, that in both of these cases, all right, there is an invisible 1 that we are multiplying each of these by in the front. Okay, now that value of 1 there means, the fact that it's positive means that both of these functions are sketched above the asymptote. Okay, so your horizontal asymptote would still be the x-axis in both cases, right? That is not a reflection over the line y equals x, it's a reflection over the y-axis. Okay, but now they expect you to be able to work with the inverse of g. So in other words, now we want to take g and we want to invert and we want to do its inverse. All right, so now I'm going to take this graph and I'm going to sketch a new, or sketch the inverse of it. I need to reflect it over the line y equals x. So it has a y axis, it has a y-intercept and no x-intercept, right? So when I do the inverse, I reflect it over the line y equals x. What line am I now expecting is going to be my asymptote? It's now going to be the that was horrible. Okay, remember x and y, swap round. Okay, so this graph is now, I can't draw it nicely on my sketch pad. Sorry, Matrix. There we go. It would look like that. Does that make sense to everybody? Okay, so that is now the reflection over the line y equals x. So here is your inverse. Okay, and whilst g is going to end up being the graph g of x equals half to the x, this one over here is going to be log half x. Okay, everybody happy with that? So easy to get confused with all these different reflections that are going on. Okay, so remember, a reflection over the x-axis or the y-axis is not an inverse. Okay, so in this situation over here, g of x is not the inverse of this pink graph that we were talking about, okay, because it hasn't been reflected over the line y equals x. Is everybody satisfied with that? And again, you can see here, originally we had a y-intercept and our x-axis was our asymptote. Now we have an x-intercept and the y-axis is now our asymptote. Okay, yeah, so in other words, it would basically end up looking like that. That's a better version of what I just tried to draw. Okay, but that would be it in a nutshell. Right, so what that means for us, Matrix, is that next time we can get into this a little bit more seriously and we can start talking about the sorts of application questions that they would expect us to be able to answer. The other thing that you need to be aware of, let me just move that down, is that there's not just 2 types of logarithmic functions, because there are 4 types of exponential functions. Do you know the other types of the exponential functions, or should I start there next time and just recap that before we talk about the other log functions?
We don't know them. So.
Do you know them? No.
No.
No. Okay. All right. That's fine. Then at least I'll start there and I'll explain that. Okay. Recap that first. All right, not a problem, because theoretically they could give you any one of the 4 exponential and any one of the 4 inverse functions as well. Okay, all right, well, unfortunately, that's it. Our time is up for today. Thank you so much for being here and being present with us. I hope you find it useful and helpful. And all the very best for the exams that are remaining. We will see you guys on
Ma'am,
Thursday. Yes.
ma'am, can I just please just move up? I want to take a quick picture of the graph, ma'am.
Sure,
If you don't mind.
there you go. Is that okay?
I just wanted to like, wait, ma'am, please just wait a bit.
No, I will. I'm more than happy to wait. Not a problem.
Yes,